Today we're going to do an elimination reaction. Probably Dr. Organ hasn't gotten to like substitutions and eliminations and all that stuff. Yeah?
He's like touched on it a little bit.
Oh, okay.
We started substitute?
Yeah, we did.
We've done like
substitution.
mechanisms, like a leaving group and
Yeah.
stuff like that. Yeah.
Oh, okay, good. Then we're synced up. Sometimes, the course sort of introduces you to, what you're going to be doing in the lab, and sometimes it's the other way around. Sometimes the lab introduces you to what you're going to be doing in the lecture. Okay, so, all right, guys, let's stop setting up and everything like that. Get over this. Won't be too long. Okay, so elimination reaction. Alright, so in general, the thing that you're looking for is, like Dr. Horgan has discussed, is a leaving group. Okay? And I'll leave that a little bit vague for right now. Dr. Morgan's touching on it and stuff. But you need a leaving group. And so the leaving group's on one carbon. It's going to leave. All right. And it'll take those electrons that's attaching it to the carbon with it. All right. And then on an adjacent carbon, so not the carbon with the leaving group, on an adjacent carbon, there is a proton. Okay? And the proton will be gone as well. Its electrons stay behind, and its electrons will make a double bond with the carbon where the leaving group was. Okay? So when you suspect an elimination reaction, you want to see is there a leaving group, and you'll learn a bunch more about like what's a good leaving group. Halogens are very common leaving groups. But so in any case, you want to be on the lookout for a leaving group. And then you want to, leaving group. And then you want to see if there are carbons that are adjacent, carbons attached right to that carbon, and then see if there's a proton that can be taken off, and then you get a double bond between these. Okay? This is not any specific reaction. This is just sort of world's most hold on. Sorry. Actually, it doesn't matter to you. I wanted this picture on the side. That is the leaving group. Your proton. Okay? You need some kind of base. In some types of elimination reactions, it's going to be a very obvious, very typically strong base. In other elimination reactions, actually, for instance, the one we're doing today, doesn't have to necessarily be like very strong or something. I mean, today it's going to be water. All right, and then in the end, you're left with an alkene. Okay? And then your base, it has that proton that used to be there. And then here's your leaving group with these electrons here. All right.
Which electrons, sorry? Which electrons? I think you just pointed to the electrons.
Yeah, okay, so this leaving group leaves and takes these electrons.
Okay.
These electrons become the double bond there.
Thank you.
Okay. There are two types. There's other types of elimination, but the two main types. maybe we are going to be doing an E1 elimination. They both need, quote unquote, good leaving groups. Okay? And you'll get a lot more clarification in the class and stuff about, you know, what makes a good leaving group. But just to put it generally, means stable once it leaves. Okay? It's not going to make some kind of unhappy anion. When I talk about this, like acids and bases and stuff like that, I always talk about happy anions and unhappy anions. A happy anion is the conjugate base of a strong acid. Okay? A strong acid isn't going to be a strong acid. Isn't going to give up that proton if it doesn't make a happy anion. Okay? So all your things with pretty low pKa's, the halogens, right? HCl, very negative something. HBr, HI, those are all really strong acids. The conjugate bases of them, halides, chloride, bromide, iodide, those are all great leaving groups. Happy anions. Okay? All right. So now, I'll point it out. Fancy dancy. See how this works. E. I may have over-engineered this. E1 mechanism. Mech, short for mechanism. Okay? So the key difference, well, I'll just explain an E1 mechanism and then I'll tell you how it differs from E2. So in an E1 mechanism, the leaving group leaves. Okay? I love stupid analogies. So in an E2, the leaving group is evicted. All right? Hasn't been paying a rent, a lot of parties, all that kind of thing. All right? In this one, the leaving group says, I hate this place, there's roaches and stuff like that, and just leaves. You're welcome. So it leaves, and this is the measurement, curved arrows, and then you get a straight line, and then you get your new intermediates that are a result, and only changing what you did right there, your curved arrows. Okay. All right. And then once you have this, which is known as a carbocation, carbon is a cation. Okay. Now a base can come in, grab that proton. So only taking the proton, so these electrons pop down there, and boom. Got that back. Okay. Not too bad. Alright. So now let's talk specifically about our reactions that we're doing today. Okay. There are little, there's a few differences, not too many differences from what from what you read in the book. You read in the book about doing this reaction with 4-methylcyclohexanol. Okay. There's actually two different starting materials we're going to do. And you're going to partner up with somebody, and you're partnering up with somebody really only for data, okay? Because one of you is going to do 2-methylcyclohexanol, and then we'll get some data about how that reaction went. And then the other one of you is going to do 4-methylcyclohexanol and see about get some information about how that reaction went. And then you're gonna share your data, but that's as much partnering as you do in this situation, all right? Okay. E1 with methylcyclohexanol. All right. Talking about good leaving groups and not so good leaving groups. OH is not a good leaving group. Okay? It makes a relatively unhappy anion if it leaves, right? Hydroxide, that's not a particularly happy anion. How do I know that's not a particularly happy anion? Because water is not very acidic, right? Water has, a relatively high pKa, in the context of acids. Okay, so OH, not good leaving group, but it can be converted to one by protonating first. Okay. So that's exactly what we're going to do here. Okay, that's 4-methylcyclohexanol. We're going to use sulfuric acid. Okay. And I won't show you the product just yet. So I'm going to show you how it gets there. Or products, I should say. Alright, so in most, if there's acid or base that's part of your reaction setup, then the acid-base chemistry is almost always the first thing that happens in your menu. Alright, so super strong acid, that'll protonate rocks. Lone pair comes down, grabs a proton. Okay. So bad leaving group, not gonna do an elimination in general. Alright, but now we've protonated it. Okay. Now it is a good leaving group. What I call this is it's basically anchored water. That's a water molecule that's anchored to this guy. If he leaves, we just create water. Remember the definition of a good leaving group is stable when it left. Well, water's heck stable. Leaves. Right.
Does it keep? Oh, yes.
I'm sorry, does it keep
I
what?
was just asking if it was going to keep its electrons when it leaves, but you see the arrow indicating that it does.
Yeah, exactly.
Yeah.
And actually, I mean, in no longer has a positive charge on that oxygen, so it must have kept those. Okay. So this is our leaving group. When you're sort of analyzing or evaluating an elimination reaction, that's leaving group. You want to look for adjacent protons. Okay. Sometimes called beta hydrogen. All right. Well, we got beta hydrogens there. We got beta hydrogens there. Okay. So now, water again doesn't have to be the exact same molecule. Grab that proton. Those electrons come down there, and we get. And this is another 2-week experiment, by the way. In this 2-week experiment, it's good to like pay a little bit of attention to the names, because we've got a whole bunch of different products and molecules and starting materials and stuff that have semi-similar sounding names. All right. So we started with 4-methylcyclohexanol. This guy is 2, 3, 4. So this is 4-methylcyclohexene. That part is the part that tells you it's an alkene as opposed to an alkane. Okay? All right. Sweet, sweet, sweet. Wait a minute. What about these protons? Do we need, couldn't those deprotonate? Right? Why didn't I draw the product of those deprotonating? Did I tell you guys a story about when I started calling people by name? Did I tell you that story? I got so many sections, I have no idea which of my stupid stories I've told. I mean, they're all great. They're all worth hearing multiple times. But I was in grad school, and I was teaching my very first class, and I was hardly older than them. So I thought, we're buddies. I'm just gonna start, Kayla, tell me, and the very first young woman that I did that to, you know how you can like scratch your forehead, but you use a particular finger? I was like, oh my God. So I'm very scared about calling Michaela. But any ideas? Actually, any ideas? Why didn't I draw the product of that one? Well, let's take a look at it. Let's try to figure out why we're not dealing with that reason.
Oh, it's the same?
It's the same thing. It's the same thing. Yeah. The ultimate, we often have to make decisions as young organic chemists about sameness. Is that the same molecule? And here it's not that hard. It'll get a little bit harder when you're doing stereochemistry in chapter 5. You haven't done that yet, right? You haven't? No, you haven't.
Yeah.
We're in chapter 4.
Yeah,
I don't think we're
It's
doing
gonna be
chapter
long.
5 minutes.
like 3 more weeks.
Okay.
Unless he starts chapter 5 next week before our exam, which might.
Well, I'm a much simpler thinker than Dr. Organ. Dr. Organ is very smart. And so you can have, this is like, you get the cliff notes first, and then you go ahead and you get like, a thorough professional job here. Okay, so, all the sameness is the type of thing you're going to have to make evaluations on a lot. And you guys saw that, and that's great. But there's going to be harder ones. But the ultimate test for sameness, remember, molecules aren't glued to a board or glued to a paper. They're floating all around and stuff. Yeah, so you can twist and stuff. It's called superimposability. Can you morph them together in your mind's eye so that everything lines up? And this is the same as that. And to mentally get there, what I always say, this is a pancake flip. Okay, you get your spatula, you come in here, boom, and it'll be right on top of that. Yeah, does that make sense? Okay, so same process.
So, the 4 indicates where the methyl is, but is that in relation to the double bond? Because when I was first thinking about this, I was like,
I'm
what?
so sorry. These masks are just
Oh,
killing our
sorry.
conversations.
So the 4 indicates where the double bond, or where the methyl group is. Is that in relation to the double bond? 'Cause
Well, it's just, that's why I numbered it for you. Whenever you, I don't know if you've named out cyclic alkanes, you gotta decide how to number it.
we just started, yeah.
Okay. And when you're numbering cyclic alkenes, the rule is you number, it's 1 and 2. Okay? So either that carbon's 1 or that carbon's 1. Okay? So how do you make the decision? You make the decision so that the substituent comes at the lowest number. Okay.
Is the lower number 1? Or is the lower number 2?
Lower number is 4. Substituent. Substituent. You guys familiar with that word when you're naming alkanes? Substituents?
Yeah, the things that are attached.
Yeah.
The little branches.
So
Yeah.
that's the only substituent on this molecule. Okay? So had I numbered this as 1,
It would have been
2, 3, 4, 5. So when you're doing these, it's going to be 1 or 2. Okay? So how do I decide? I decide so that the very first substituent, the very first branch, thing hanging off, comes to the lowest possible. Okay? All right, and we're going to make some more cyclic alkenes here in a second, so you can really solidify that one. Oh, I was going to show you. That's the one when you teach that rule, and then you're in a bad mood, and you're mad, and you're making the test, and so you throw that on there. Yeah, take that. Okay. Oh, which one do you put carbon 1 and carbon 2? Is that carbon 1 or is that carbon 1? Left or right?
Right.
Oh yeah, see? Yeah, it feels good because in a bad mood. No, that's carbon 1. And then you go all the way around. Why? Because that's the first substituent. Even if I was in a bad mood, I'd make that one and I'd go, come on, don't be a jerk. And then I would make it. All right, anywho.
Let's have Dr. Horgan as in a mood when he makes our example. Because I don't want questions like that.
Well, I mean, you guys haven't even had naming of cyclic alkenes, so don't, I mean,
We haven't gotten to-
cyclic alkenes, so don't worry about it.
Yeah.
You got plenty of time. It's not, for this, for our purposes, you don't really have to know why they're named that, you just know they're named that, so you can differentiate all these different things. All right, so like I said, some of you are going to use this guy, the 4-methylcyclohexanol. And some of you are going to use 2-methylcyclohexanol. All right, so same mechanism. Fat leaving group gets protonated by the bazooka of acids. Okay. Get that guy. This guy. Now, you guys draw the problem. What's that? I'll catch the notes. What did I say next? I'll write it down. Get a little obsessed with my different pen colors. I'm a little busy sometimes. The day they just, this is the first semester ever they've had purple. It was like a big day in my life. Sad as pathetic.
Best day ever. Christmas.
Well, I mean, that week, easily, hands down. Stop using green. It's like visible ink for students trying to keep up with the lecture.
They're like,
All right,
sorry.
are we doing okay? We got it? Who we got it? Okay. So look for our adjacent. Remember, there's where our leading group was. We look for adjacent carbons. Boom, boom. H2O. Okay. Sorry. Alright, is that what everybody got? Anybody get a different answer? No? There's one more answer. You get,
we're from
and there's an
outside.
expectation here, okay? Yeah, we've got another adjacent proton. Don't forget about that guy. When you learn skeletal structure in that first week or 2 weeks or whatever it is, it's one of those things students learn easily, and then they just kind of, yeah, I got that down. I'm going to kind of, you got to be able to look at these things and in your mind's eye see the protons, even though they're not written in. All right, so yeah, and that can get deprotonated too. Here, do color this one. Boom.
Is that different than the other one that we got?
You tell me.
Yes.
Superimpose. Try to float it out here in your mind's eye, and so that everything lines up. Can you do it? No, impossible. And if you can't do that, if you can't superimpose them, they're different compounds. And you're going to get to ones that are more subtle than that. A heck of a lot more subtle than that. Okay. All right. Why don't you try to name it real fast, just for fun? For giggles?
Which one do we want to name?
Both.
Both.
I don't know why today I'm so tempted to start calling my name.
Do it.
But I'm very sensitive, so I don't like any flip talk.
Challenge accepted.
I could call you. There's no way you look.
What?
You just gave me a look like, oh yeah.
Sorry, I was like winking, but like looking
Okay,
at you.
no, I'll just shut up and let you nail it. Okay, how you doing? You know that the alkene carbons are going to be 1 and 2. You number it so that the substituent comes to the lowest possible number. So I can start here and go 1, 2, all, no, 1, 2, 3.
3 methylcyclohexene.
Wait, why didn't you do it the other way? Were you?
Because it takes longer to get to the branching group.
Here it comes at 3. If I had gone 1, 2,
Oh.
3, 4, 5, 6.
Oh, you have to do 1 and 2 on the double on.
Yeah.
Oh, got it.
And the other one is the 2-methyl.
What's this name?
The 2-methylcyclohexene.
I just showed you the tricky one. The carbons
It's
are back.
right, right?
But it's
Because-
1, exactly.
Because it's in the same spot. So when you write the name, do you have to say 1-methylcyclohexane? Or do you
Yeah,
have
you
to
gotta
say?
be on. The whole point of naming is that the name tells it to you unambiguously. Okay? You know it perfect. And it's critical. You guys know the. Did I tell you the thalidomide story? Yeah, stuff like that. There are 2 types of thalidomides. Okay? One is a medicine that was invented for morning sickness for pregnant women. Okay? There's another type of thalidomide. The only difference, they are isomers, so you know they have all the same connectivity, or they're all the same molecular formula. Okay? They are not constitutional